Sweet. Okay. Hello, Earth Science, and welcome. This is the first chapter of Earth Science. So we're going to do a lot of introductory things today. I apologize that I don't have my picture up in the bottom right. I will have that in future videos. Just had some problems with technology this morning. Alright, so what is Earth Science? Earth Science, this is the branch of science that deals with the physical constitution of the Earth, its atmosphere, the waters on it, the area beneath it, and the core and the mantle. We're talking about the atmosphere. There's four main branches of Earth Science. There's geology, meteorology, oceanography, and astronomy. And we're going to cover all of them in the course of this course. So the first, what is geology? And we're going to talk about these in much greater detail later. Today is kind of just a overarching welcome to Earth Science. Here's the gist of what we're going to talk about. Geology is the science that deals with the Earth's physical structure and substance, its history, and the processes that act on it. So this arch here, some of you may have been around Arch National Park, some of you might have seen stuff like this before. This is caused by wind erosion, but there's many other features that affect Earth's surface. Meteorology, this is the study of the atmosphere. It focuses on weather processes and forecasting those weather. This device over here on the right hand side is a barometer. It has temperature, it has humidity, it has the actual barometer on it, which is the change in pressure. And these all affect how the weather is going to be outside. Oceanography. This branch of Earth Science deals with the physical properties and phenomena of the sea. So our example here is this warm and then cold big old water belt that most of the water in the oceans are going through. This is the conveyor belt of the sea, so when we talk a lot about like trash in the ocean, it's usually riding on this conveyor belt, getting stuck in the Pacific garbage pile, which is out here. Astronomy, this is the scientific study of celestial objects, things as stars, planets, comets, galaxies, and phenomena that originate outside of Earth's atmosphere. So this is the one Earth Science kind of field that isn't Earth Science. It's more of a space science, but we still consider it inside of Earth Science. Because these things do have effects on the Earth. We get comets that hit the planet, our tides are affected by the planets, and someday we hope to go and visit and explore other planets. So using a telescope to map the craters of the moon over here is an example of using astronomy. So what's the history of Earth Science? Why do we have Earth Science? Long ago, we had scientists who would study very specific Earth processes, looking at just the formation of mountains. Or another one would look at just the life on those mountains, studying the deer and elk and the plants and the berries. And a third scientist might have just looked at just the ice that's forming on the peaks of these mountains. And there wasn't a lot of communication between these three. They were just kind of all independently doing their own thing. Well, in the 70s, 50 years ago, we had these chlorofluorocarbons, which were awesome, wonder chemical of the day, peak modern science, space age technology. And they were used in air conditioners and aerosols. And they were great in air conditioners and aerosols, but it was when they rose up into the atmosphere, because they were super stable compounds, that they became a problem. And they started to degrade into ozone. What is ozone? So atomic oxygen, which is very rare, is in its singular form here, one atom of oxygen. Diatomic, which is the stuff we breathe. This has two oxygen molecules, and then ozone has three. And ozone forms as diatomic oxygen, makes it far up into the atmosphere and gets hit by sun. It's turned into atomic oxygen, which then go and bond to another diatomic oxygen. It's a very cool process. Ozone's toxic down on the ground level to us, but we like it up in the atmosphere. So this ozone forms this protective layer around Earth. Without it, we now have lots of UV radiation from the sun. And the CFCs degraded lots of ozone into breathable oxygen, which is good to have breathable oxygen, but not up in the atmosphere where we can't access it. We need it down on the ground, and ozone up high. So the less ozone we had, the more radiation we had. And this led to an increase in skin cancer cases globally. So we instituted a ban on CFCs. And these nations that came together were most of your first world countries and developing countries. There are a couple outliers that still use CFCs, but not a significant amount of the portion. It's still taking years, however, for this ozone from 2008 here to 2015 to really start to heal back up. We got a long ways to go until we get back to like our 1979 model there. We got a long ways to go, but we're getting closer. So because of this and some other things going on, but CFCs were the big driving force, we have the rise of the Earth science system. So now scientists are realizing that Earth is more than just a collection of parts, and using lots of technological advances like satellites to see Earth from space and submersibles to see the bottom of the oceans, and programs like GIS, which is the Geographic Information System, which allows for interpretation of data and to see how Earth changes over time, to see how climate changes over time, to see how rainfall changes over time, or plant growth, or tree cover. You can look at all these things using GIS. In Earth science, we use a lot of models, which are representations of an object, a process, or a phenomena. You want to take something like the globe, the entire worldwide globe, and put it on an actual globe, something smaller that you can hold in your hand, you can look at, you can make inferences and observations about it without having to like fly all the way over to India to look at the topographical or mountain ranges of India. You can just look at them on a globe, which is cool. This is good stuff. So what is a system? A system is a kind of model, and it's a part of the universe that we can study separately. So an example of something we can study separately is, for example, whatever room that you're in as you're watching this could kind of be like, that room could be a model. You could make inferences about it. If you built a fire in the middle of it, it would get warm. If you open the door to the outside, if it's in winter, it would get cold. This system, you can make inferences about it, and you can actually study what's happening inside of there. If you let loose a population of butterflies, you could count the population of butterflies, you could keep track of them, you could see if they're having babies. There's all kinds of science that you can do inside of whatever system you're in. Time is a variable. Variables are something that we can test for. Time is an important variable in Earth science, both short scale, as in years, or long scale, as in millions of years. There are two types of system. There's an open system and there's a closed system. Closed systems allows the transfer of energy but not matter. An open system allows the transfer of energy and matter. There's a little distinction between the two there. So here's an example of a closed system, which is no matter is being transferred, just energy. So this sealed jar here, while energy can get in and out, nothing can get in the top. That's the important here. It's a closed system. There's no new stuff. Another example would be a submarine, and we even consider the Earth as a closed system, as we're getting very little stuff in and not losing anything because of the gravity of the Earth. There are some select instances where we have like comets and asteroids, and we lose some hydrogen due to solar heating, but it's such a small amount in and out that we consider ourselves a closed system. Now, open systems, on the other hand, these are matter and energy are transferred freely, so you can get matter in, matter out. In the example of this open jar over here, you're getting energy in from the sun and you're getting energy out, but you're also getting that nice lemon drop in. And if it gets too hot, that tea will start to evaporate out of that glass. So there's this ability for matter to travel freely inside and out of the environment on these ones. So an open jar, a fish tank, an island, all of these things are open systems. Now, planetary systems. This is Earth. We're a planetary system. We absorb our energy from the sun and lose it back into the space as energy. Like we mentioned earlier, it's not entirely closed. We do get some meteorites in and hydrogen atoms lost, but the mass of the Earth stays constant. So what is matter? Just a real quick review here from some rudimentary science concepts. Matter is defined as anything that has mass and takes up space. So a desk, a glass, all of these things are matter. You have a mass and you take up space. Mass is the amount of matter something contains, and we measure it in grams. And then weight is the force by which a body is attracted to Earth through gravity. Weight is different on the moon versus on the Earth versus on Jupiter. Your mass stays the same no matter where you are in the universe, but your weight has the ability to change, depending on how much gravity is being exerted on you. So humans in the Earth. The ozone depletion is one example of how we affect the planet. There's a lot of others. We have hydroelectric dams and irrigation changing river systems, global warming, plastics in the ocean, and recycling. Not all the changes we affect on the Earth are bad. Recycling is awesome. We are taking stuff that we have used and we're reusing it because we only have so much aluminum on the planet. So we need to make sure that we maintain and use all the stuff that we have. There are 4 spheres on the Earth. Earth is the only planet in our solar system that has life on it that we've discovered so far. We're kind of partial to that. So first is the atmosphere. This is the gaseous envelope that surrounds Earth. It's composed of a mixture of gases, nitrogen, oxygen, carbon dioxide, water vapor. We as living things get our oxygen from the atmosphere and breathe out carbon dioxide. And then carbon dioxide, so ozone is one we've already talked about, but also water vapor is really good at blocking the sun's harmful rays, preventing UV getting through to the. We get water vapor in the atmosphere, and this results in areas of high and low humidity. The air up here in northern Idaho, where I am, is a lot different than the air in the southern states, around the equator. This varying degrees of atmospheric pressure causes winds, which can cause erosion and storms and waves and tornadoes and all these very cool phenomena. But because of this uneven heating is how we get these big pressures. Our atmosphere is the only one in the solar system to contain free oxygen. You don't have to hunt down oxygen. It's readily available for you when you take a breath. The moon has no atmosphere. It's too small. Other planets like Venus and Jupiter have atmospheres. This is a picture of Venus here on the right-hand side compared to Earth. They're very similar in size. They both have these like white wispy clouds. But Venus is more carbon monoxide and methane based, and it is very toxic to anybody who would be there. They also have much more atmosphere. They have a higher atmospheric pressure. The human lungs would be collapsed if we were to live on Venus. So it's a good thing that we live on the blue one. Our second sphere is the geosphere. This includes rocks, mountains, beaches, and all the other physical features of Earth, not including water. Water is its own sphere. We're going to talk a lot about water in this class. The geosphere also is the layers of the feet beneath your feet. Layers of the earth, beneath your feet. The crust, the mantle, the outer core, the inner core. All of these parts are things that are interest of study to the geosphere. The mineral resources that we find today are mined from the geosphere. We get stone and concrete from the geosphere, and it's constantly changing. We have volcanoes erupting to create new land. We have mountains being eroded, and even Earth's continents are slowly in motion. The hydrosphere. This contains all water at or near the Earth's surface, including oceans, lakes, rivers, and groundwater. We also have water trapped in ice and snow. Only 3% of Earth's water is fresh water, and of 70% of that 3% is frozen in glaciers. That means we only have about 0.5% of that 3 is usual fresh water. And luckily, all the water on Earth is continually cycled, so we're making new fresh water. It's just at a very slow rate. The biosphere. This is all living things existing in this sphere. Single-celled bacterium all the way to the blue whale, which is the largest animal to ever live on the planet. This is also the sphere that we primarily exist in. We affect the other spheres, but this is the one where we live. So all the spheres are interacting all the time. Some changes happen very fast, like a cold snap is killing a crop of potatoes, or on this picture over here is killing this corn. And some happen much slower. Rivers eroding rock to form a canyon, that takes a long time. It takes a long time for canyons to form like that. On the Earth, we have lots of cycles. Cycle is a sequence of events that repeats itself. We have 3 that we're going to talk about today. Some repeat often, and some are much, much slower cycles. The water cycle. This is the continuous circulation of water through the hydrosphere. Continuous, spelling error here in the slide. Most of Earth's water is in liquid form. When the sun shines on a big body of water, it causes some of that water to evaporate, and that escapes into the atmosphere as vapor. That vapor then cools as it rises in the atmosphere, and it condenses to form clouds. As these droplets grow, it starts to rain, and if it's cold, you can get sleet, hail, or snow instead. The water cycle has some runoff. This is when rain falls to the earth and it lands on the ground, and it doesn't go into the ground. When it goes into the ground, it's called infiltration. This runoff will flow into streams and eventually will make its way into rivers that eventually travel back down to the sea. Some water soaks into the ground and doesn't become groundwater, and it becomes doesn't become runoff, it becomes groundwater. And some water is re-evaporated before it even makes it back to the sea. It might be in a stream, and it's going down to the ocean, and it gets evaporated out of the stream or river or lake. Some water is breathed out by plants. We call this transpiration, like they're transpiring this water out of their leaves and roots and stems. Evapotranspiration, this is a big spelling bee word. This is the cycling of water vapor into the atmosphere by transpiration and evaporation. So it's these two processes together that we call evapotranspiration. And the water cycle, the important thing to remember about this is when it returns to the ocean, one cycle is complete, and now it's going to go through and do the same thing over again. It's going to evaporate and precipitate. It's going to evaporate and condensate and precipitate. Maybe get stuck in a tree and get transpirated. Water has traveled through this cycle in Earth millions of times. All the water that we have today has been around forever, so the water that you're drinking, high probability that a dinosaur was enjoying it some 35 million years ago, 350 million years ago. The carbon cycle, this is our first biogeochemical cycle. Bio meaning life, geo meaning earth, chemical meaning chemical. Carbon cycle focuses on the element carbon, which on the periodic table is designated by a C. It is the building block of life, and it's present in all organic materials: coal, oil, plants, animals, steak, that's an animal, part of an animal, but carbon is present in all living organisms. It can be found as a solid, such as this picture on the right here of graphite from a pencil. It can be liquid methane, or it can be gas, carbon dioxide. As carbon dioxide enters the atmosphere, it can get there in several ways. Animals can breathe out as carbon dioxide. Organisms can break down decaying organic matter, like bacteria and maggots. When carbon-based materials burn, like a wood stove, carbon dioxide is released. Volcanic eruptions release a lot of carbon dioxide into the atmosphere. And we also get carbon dioxide that diffuses out of the ocean's water as those waves are crashing onto the shore. We get carbon dioxide into the atmosphere, but hopefully we get some of it out. The Earth is pretty good at it. Plants remove carbon dioxide during photosynthesis. They then release oxygen as waste, which is awesome for us oxygen-breathing organisms. These plants that remove the carbon dioxide, that carbon that gets stored in their body as carbohydrates and sugars through photosynthesis. In addition to plants, phytoplankton are also using photosynthesis, and they're releasing oxygen as well. So they're creating more of that awesome oxygen in the ocean. These phytoplankton, a picture here on the right of some different shapes and sizes and colors, they're eaten by other animals. Those animals then use that carbon that was stored as energy, and then they store it inside of themselves. As these phytoplankton die of natural causes, they sink to the ocean floor, and this carbon is stored on the ocean floor. Any place we have carbon stored, we call it a carbon sink. So when we talk about oil reserves or these limestone deposits where there's a bunch of shells that are on the bottom of the ocean, these are all different ways that carbon is stored. The motion of ocean waves dissolves carbon in seawater, which is then converted into lime, which is a major component of seashells. The ocean removes 40% of the carbon dioxide created by fossil fuels. Sorry for this little cutoff there, but the ocean removes 40% of the carbon dioxide created by fossil fuels. So the ocean is really important for our planet, for our well-being, for the future of global warming and climate change. When plants and animals die, their tissues are dissolved by bacteria. This solid carbon gets dissolved into CO2, and methane, and the cycle starts all over again. That carbon dioxide is reabsorbed by a plant, turned into glucose, or some kind of sugar eaten by an animal, so on and so forth, over and over again. Some things in the carbon cycle happen very fast, like organisms live, die, and decompose. That's very fast. Even like humans, 86 years is a very small amount of time in the geological time scale. Fossil fuels formation, this is a very slow process. It takes a long time for a plant or animal or vegetation to die, get stuck in this low oxygen environment like a marshland. And the carbon in the tissues plus time and low oxygen equals fossil fuels like coal and oil. While it takes a long time to build up these reserves, it takes us very, very little time to burn and release that carbon dioxide. There's a lot of energy stored there, a lot of carbon, but it does release a lot of carbon dioxide and they're burned very quickly. We cannot make them as fast as we are using them. So does the amount of carbon change in Earth's system? No. It's staying constant. It's just being converted from one form to another. This cow's breathing it out to CO2. That CO2 is getting stuck into the ocean. Phytoplankton are using it, creating oxygen. You have rock formation. That rock formation is getting burned as coal. There's all kinds of ways that this carbon is being transferred from one state to another. Our last cycle we're going to discuss is the energy cycle. This is the one when we talk about Earth's battery or where we get our energy from. The energy in the Earth stays constant, so the amount of energy going in and the amount of energy going out is going to be equal. It's kind of this delicate balance of life. So where do we get our energy? Well, most of it comes from the sun, 99.985%. Most of it comes from the sun. We get a small amount from some other sources, which we're going to talk about in a little bit, but the energy from the sun is called solar energy. It drives the winds, the ocean currents, and the waves. It is the main source of energy for weathering rocks. The other energy sources we get are geothermal, 0.013%, and this is heat from within the Earth. Like, this is stuff that powers volcanoes, geysers, and earthquakes. Still really big, awesome, cool processes, but there's not as much energy powering them as the sun. And then tidal energy, which is even smaller at 0.002. This is the result from the pull of the moon and the sun on Earth's oceans, and it's small compared to the sun's energy, but it's still powerful enough that over the millions of years that the Earth has been around, it's slowed down Earth's rotation. We now have the 24-hour day instead of the 16-hour day, which was something that the predecessors on this planet used to experience. So where does this energy go? 40% of our energy is reflected back into space without even being used. Just hits the atmosphere, hits the ground, is bounced right back up. The remaining energy, the remaining 60%, is what we use within our Earth system. It might be used to make water evaporate. It can be changed into winds and waves. It can be used to store in plants and animals. Fossil fuel is just really old solar energy that's just been sitting around for millions of years. So all this really cool stuff that we use and happens is part of this sun giving us energy. Now, when we talk about energy, we got to talk about the law of thermodynamics. This is a branch of science that deals with how energy is converted into different forms of energy. The first law of thermodynamics, we cannot create or destroy energy. It can only be changed from one form to another. So this is when you're outside and the sun is beaming down on you, you're getting this radiant energy from the sun being converted into heat that you could feel. Or you might have a solar panel out there and it's catching that radiant energy and turning it into electricity, which is another form of energy. That electricity might be used to run the heat in your dryer, might be used to help pump water as a water pump. There's lots of different, might be used as electrical energy to keep light, which is light energy, and heat. There's lots of different ways to change energy from one form to another. The second law is when it's converted, energy is converted from a more useful, more concentrated form to a less useful, less concentrated form. So every time we convert energy, we're losing some as heat, as radiant energy, etc. So when a plant is getting sunlight, it's not catching all the sunlight, it's losing some of that. It's going from more concentrated to less concentrated. When that plant is eaten, not all the energy is consumed. So it's going from more useful, more concentrated to less useful, less concentrated. And if you're familiar with it, this is the kind of the concept behind entropy and the this randomness of the universe. Energy can never be replaced completely. We always lose some energy. Usually, the most common way is as heat. So Earth's surface is not uniform. We have oceans and deserts and grasslands, forests, cities, and glaciers. All of these reflect light differently. And we call this albedo. This is the percentage of energy that is reflected without being changed. For forests, there's a low albedo. They're absorbing most of the sunlight, only reflecting 5 to 10% of it. High absorption rate. Freshly fallen snow, on the other hand, high albedo, reflecting 80 to 90% of sunlight. Very low absorption. So how do us as humans affect the cycles? Well, for the energy cycle, planting a forest will absorb more energy, and more of that energy will be stored inside of trees instead of just bouncing off the ground. For the water cycle, we irrigate fields, we dam rivers, we do all kinds of things to affect the water cycle. Pollute. The carbon cycle, when we burn fossil fuels, we release carbon dioxide into the atmosphere. Planting forests helps reduce that carbon dioxide that's getting into the atmosphere. There's lots of different ways we affect these cycles as humans. We have a very profound effect on our planet, and it's something that when we talk about things in this class, we'll talk about how we can do better, things that are already being done, and we'll be talking more about these cycles just in general. This is the end of Chapter 1. Thank you for watching. Hope you have a wonderful day.